In this sequence of videos, we're going to talk about some challenges that come up in the data science workflow. Things that can go wrong, pitfalls to be aware of. So we'll start off by kind of outlining what is the data science workflow, and this will maybe be helpful for you on your project since you'll be using this kind of workflow. Then I'll kind of like dive in a little more detail around like data and modeling workflow, talk about a couple issues that come up, and then end with 2 case studies. And so as part of today's lecture, it'll be a little different from usual. There'll be 3 points where I want you to stop and write down your thoughts on the worksheet based on, like what's in the videos, and also for each of the 2 case studies to write down your thoughts. And we'll spend most of discussion actually talking through and walking through the case studies, walking through things that can go wrong with your thoughts. So, it'll be a little more interactive. It'll be pretty fun. Highly encourage you to come to discussion this week. All right, hope you enjoy the videos. In this video, I want to talk a little bit about what the data science workflow looks like so that we can identify where the problems will come in and what the challenges we're going to face will be. So generally, you're interested in using data science because you have some question about the world that you want to answer, or you have some goal that you want to accomplish. So we almost always start with a question or a goal, right? If we're trying to build a product, then we want, our goal is usually oriented around how do we make a product that meets the needs of our users? If we're trying to, go about some scientific endeavor, then our question is usually a scientific question. How does the world work? How is this particular thing in the world related to that particular thing? So generally, this is the starting point for any data science analysis, whether, it's sort of, no matter what domain you're working in. So it's really important to make sure that you have a clear formulation of what your question is, or what your goal is, and how you're going to answer it. Then, since hopefully this is a data science oriented question, then the next step is usually to go out and obtain some data. And these steps don't necessarily happen in this order. Sometimes, you have a certain data set available to you. And so that data set kind of brings about questions. And a lot of times when you go out and get data, then you kind of have to refine the question you can get. Maybe you don't have all the features that you thought you might be able to get. Maybe once you obtain the data, you realize that, obtaining some data is harder than you thought. And that kind of changes the questions you can answer. Or maybe you thought some data is easier to get than you thought, which kind of affects the questions you can answer. And so a lot of times, once you obtain the data, there's some refinement of the question or goal that ends up happening. Okay, then once you have the data set, then the next step is to conduct some kind of EDA, right? You want to go to your data set and do some exploration, look at the different variables, understand what's numerical, what's categorical, what the distributions are, what the relationships between the variables are. And this is the sort of thing that you've learned in Data 100, that you've done a little bit on the assignments in this class that you'll be doing in the project in this class. But generally, this is kind of a common pattern, right? You'll always want to do some EDA. And typically, after you do the EDA, then maybe that a lot of times that'll raise more questions than it answers, right? You'll say, well, this is interesting. There's, this particular categorical variable never takes on this value that I thought was supposed to be common. Why is that happening? And so maybe you'll need to go back and obtain the data. A lot of times, if you're, a data scientist working with a domain expert, then, the EDA might reveal things you need to go back and say, well, wait a minute, I thought these 2 variables are supposed to be correlated, but I'm not seeing any correlation. What's going on? And so a lot of times that requires you to go back and talk to a domain expert, refine your assumptions, and deepen your understanding. And a lot of those skills are skills that unfortunately are beyond the scope of this class, right? We can't say, in this class, learn how to carry out a full research project. That's sort of the goal of the project, but even then, it's a relatively controlled environment. We're giving you the data sets, as opposed to a lot of real world data science problems where you'll be working closely with somebody who has a deep understanding, or you might be that person with a deep understanding, and you need to bring both your understanding of the data and the world and your data science expertise. So, sometimes this leads you to go back and obtain more data. And sometimes it even might lead you to go back and reformulate the question. You might see, oh, the data is nothing like my initial assumptions led me to believe, and so I need to completely reformulate my question. Or if you're building a product, you might say, well, actually, based on the data, this particular formulation of the product will not meet the needs of my users at all, or will not drive any value for my business, will not answer the question I'm trying to answer. And so let me go back and reformulate or adjust. Then once you've done your EDA, then the next step is to actually do some kind of model or inference, right? So now we have EDA, and then you're actually ready to do some kind of model or inference, right? And this is where a lot of the techniques that we've taught you in this class come into play, right? So, maybe you formulate a Bayesian model. Maybe your question is a causal question and you need to do your inference needs to be a causal inference. Maybe, you get some sample data that's, available offline, but your product is going to be deployed in an online setting. And so maybe you need to use bandits or reinforcement learning. Either way, you generally will have some, data set. You can try something, you test your approach, you try it out on the data. And then what comes out is some decision, right? And again, we've kind of said at the beginning of the class that we're going to focus a lot on two of the big ideas in this class are, number one, decision making. How do we go from doing data science analysis, models, inference, to actually making decisions? And anything you're going to do in the real world, you'll need to make a decision on. We'll need to make a decision, or your inferences will be used to make decisions down the road. And so it's important to keep in mind this entire workflow and life cycle, and to kind of investigate the things that can go wrong. And of course, there's I'm not going to draw all of them, but there's a lot of arrows that go kind of back and forth between these steps, right? You imagine that you apply your model, you apply your inference, and you say, oh, well, actually, I realize that these variables, there's this other confounding factor I didn't take into account. So maybe I need to go back and go and obtain a little more data. Or maybe, when I say, oh, I've, done this, I make the decision, and the decision actually ends up being something that, let's say you're building a product that doesn't actually provide value. And so you have to go completely back to the drawing board. So these are the kinds of things that happen a lot in real world data science workflows. This pattern sort of reflects what we'll expect you to do on the project in this class, right? We're expecting you to formulate a question, to work with either one of the data sets that we provided you, or to go out and obtain your own data set or use a data set you're familiar with, conduct the exploratory data analysis that you're going to do some kind of model inference techniques you've learned in this class to answer those questions, and then kind of report back to us, and you write it in your report. What are the decisions that could be made based on that information? So this is a common workflow, and in the next few videos, I'm going to dive a little deeper into specifically the data kind of model inference side of things, and think about where some pitfalls might happen with some examples. So let's talk a little more about the specifics of the nitty-gritty of like data, model inference, pipeline decision, and that part of the pipeline. But before I do, I want to just re-emphasize one more time that it's really important to consider that in the context of the broader workflow, right? Make sure that when you ask the questions that we're going to ask, that you do so in the service of thinking about what is the question you're really trying to answer? What is the goal you really have? And a lot of times that question is not just, is this variable correlated with that? It's, can I make some treatment can I understand a relationship in the real world that will help me make better decisions about how to provide health information to people? Can I, make some decision that will help me build a product that will, improve the lives of my users or drive more revenue for my company, or what have you. Okay, so this is our kind of high-level workflow. And so let's talk in a little more detail. So we have data, right? We get some kind of data. And where does that data come from? That data comes from the real world, right? There's a world, we have some data. And then usually what we do is, we kind of like explore the data, and then we split our data into training and validation. And into test. And then we'll fit model. And we've seen different kinds of models we can fit, right? We can fit a Bayesian model, we can fit GLMs, we can fit non-parametric models. We've learned we can fit neural networks. We've learned of all kinds of different ones, different types of models that you can fit depending on your problem. And then usually we'll evaluate on the test data and say, okay, how good is the model? And so there's kind of a bunch of different steps here. And in the next few videos, we'll break down what happens if things go wrong in each of these steps. Before I start blabbering about all the different ways that things can go wrong and all the different things you can do, I want you to take a few minutes to think about ways in which things can go wrong. So think about kind of real world settings where you've seen data science use, you've seen people use regression or use hypothesis testing or use model fitting, and things have gone wrong. And try to see if you can link it back to these two diagrams I've shown you. Are there ways in which things have gone wrong that you can point to specific boxes and arrows in these diagrams where things broke down? So I want you to take 5 minutes to write down anything and everything that comes to mind. So that's the first question on the worksheet. And so you can go ahead and open that up. And I'm just going to let this video run for 5 minutes. And I want you, until this video ends, to write down every possible thing you can think of in that worksheet. All right. Hopefully you had a chance to write it down. You're welcome to pause and continue if you have more ideas. And now in the next few videos, we'll go through some examples of where things go wrong and some kind of ways to be mindful of these things and prevent them from happening in your real world data experience. So I want to start off by talking about some ways in which the data that we collect might not be a good representation of the world. And to do this, I want to use an example that you're probably familiar with, which is using maps, right? These days, if you have a smartphone, you have a Maps app. Usually, a lot of times that's from Google, and you tend to assume that Google Maps tends to know about traffic. And how does Google Maps know about traffic? Well, they have a lot of people using Google Maps, right? And so you imagine that if you're using Google Maps, then Google knows that, hey, and you're driving down a certain highway, they know, aha, this person is driving down this highway. If there's hundreds of people all on the same highway, all using Google Maps, and none of them are moving very fast, then Google knows, hey, there's probably a lot of traffic over there. So, generally it's a safe assumption if you're Google to assume people, tend to, or traffic data tends to be well represented by volume and number of smartphones using Google Maps in that area. Well, so there's this guy in Germany who Google Maps ended up routing a lot of traffic right by his street, and he was not particularly happy about it. Right, there was a lot of extra traffic, a lot of extra noise, and so on. Wasn't particularly happy about it, and so he was wondering is there a way that I can hack this so that people don't end up getting routed by my street. And so I wanted to take a second and think about how might one small person go up against the entire system of Google Maps. Thought about it? So this is what he did. So you can see that there's this, the route I'm showing is on the left. And what he did was he bought an entire wagon full of smartphones, and on each of them ran Google Maps and loaded up some directions. And it turns out that there's a whole bunch of smartphones all running Google Maps all on the street. And then Google suddenly thinks, hey, there's a lot of traffic there. Now, is there actually a lot of traffic? No, right? But this is just a warning that sometimes the data that you collect may not be an accurate representation of the world. And sometimes this may just be because, the data don't reflect the world. And in some cases, it may be, in this case, like straight up adversarial, right? Where you're trying to collect data, but you have an adversary who's trying to oppose that data collection. Now, of course, which side you're on obviously depends on your own personal views here. But this is kind of a funny example of a way in which the data might not accurately reflect what's going on in the world. In this video, I want to talk about ways that the model that you fit could be wrong. And we'll see this kind of a few different ways. The first is model misspecification, which is basically a way of saying that sometimes your model is not a good fit for your data. Maybe your data has some kind of nonlinear relationship and you're trying to fit a linear model. And again, at this point, we're assuming that the data are a good reflection of what's going on in the real world. In a few minutes, I'll talk about what happens if that's not true. But for now, let's say that the data is a good reflection of what's going on in the world. And you have a nonlinear relationship. If you have a linear model, then probably not such a good thing, right? And we've kind of seen examples of this before, right? When we tried using Poisson regression on data that was over dispersed, right? If there's like a lot of variance in the data, the Poisson regression kind of assumed that the mean and the variance are kind of the same. And that didn't work so well for data where the variance, variance is much higher. And so in cases like that, your model is not a good fit for your data, and you're going to end up making the wrong predictions. A lot of times this tends to happen with, in case, if you see it in, if you can usually see this issue in the training and validation data, this tends to be because you're underfitting, right? What does underfitting mean? It means that your model has relatively high bias, right? Remember, we kind of talked about like the relationship overfitting, underfitting, bias, variance, and we talked a little bit about non-parametrics. But generally, if a model has high bias, simpler models tend to have higher bias, right? On average, if we look at like how the prediction from the model versus the average value of the data, the model is very simple. It tends to have high bias. And you can usually see that by relatively poor performance on the training data set. Now, that's kind of model misspecification, underfitting, that family of things that happen. Another thing that could happen is that your model is a bad fit because it's too complex. And this is generally called overfitting. This is where your model, let's say you train a really deep decision tree on some data, and it does perfectly on the training set. Now you try it on the test set, and suddenly it doesn't do well because it's essentially memorized all the individual examples, right? If you have like a one nearest neighbor model for something, then it's essentially just memorizing all the examples in the training set. So generally those models, we say tend to have high variance, and we saw, with random forest, we can kind of like average and kind of reduce it that way. And so there, we saw that in when we could use the test data. Now, another thing that could happen is something called, and this is a little more interesting and something that happens a lot in the real world, is distribution shift. So this is something that happens in the real world. I've definitely encountered this quite a bit in my own data science experience, where you collect some data, you think it's a good reflection of the world, you build some complex model, you look at the training error, it's great. You look at the test error, it looks great. You kind of like tweak, adjust it. You get really good training error, really good test error. And then you go and you use your system in the real world, right? In, the settings I've seen, you build a model, you kind of like have some notebook, you're like playing around with the model. And then you go and, you put it in a production software system. And it turns out to suddenly do really badly. And why does this happen? This happens because of something called distribution shift. So over here, what we're assuming in this diagram, we're assuming that, the fact that we just take our, data that we got from the world, the data set, split it into training, validation, and test, meant that we're saying, okay, like the training data, the test data, both of those are a pretty good representation of the world. And so if the model does well in the test data, it's going to do well in the future. But in most cases, what you're going to see is, once the model goes into the real world, what you're actually applying it on is new data, right? It's not the same data that you're working with before, right? Let's say you train a model to predict number of people who attend a park, right? Based on, population in the neighborhood, rents, housing prices, and so on. You try to predict how many people go to the park. Now, you train that on data from 2019, and then you apply that model in March and April of 2020. Well, your model is going to do really, really badly because, in March, April 2020, that was the kind of the early days of the pandemic, right? At least in the US, where everything was locked down, attendance was probably a lot lower. And so, your model makes a lot of assumptions. So you could have done a great training, validation, and test split, but if the new data reflects some changing patterns in the world, then your model is not going to capture that. So what are ways you can avoid that? Well, one thing you can do that is to ensure that the test set captures some notion of newness. Right? Maybe if you're training a model on medical data and you want to predict, trends, maybe you look at your training and validation data have patients from 2019, and your test set has patients from 2020, and see how well you do. Or your training and validation have data from 11 months, your test set is the next month, right? Whatever setting that your model is going to be used in the real world, it's important to capture that in your test set, to avoid this issue of distribution shift. And why is it called distribution shift? Because it's essentially saying that, well, the distribution of the data that the model gets applied to in the real world this distribution and this distribution are different, right? So there's a shift in the distribution of the data from when we train it and evaluate it and all that to when we use it in the real world. And this happens a lot. This happens in pretty much every real world data science machine learning problem that I've seen. And so it's important to kind of account for it. And this also happens in scientific settings as well, right? There's the example of the Framingham Heart Study, which is a huge study of people to try to understand factors leading to heart disease. If you took data 8 relatively recently, you probably did a project on this. And what they found was there's all these things that are like good predictors of whether someone's going to get heart disease. But then it turns out that the study was conducted in Framingham, Massachusetts, and Framingham, Massachusetts is overwhelmingly white. And so a lot of the conclusions that they drew ended up not necessarily being accurate for folks from other racial groups. For example, they needed to have some significant adjustments and changes made for Hispanic folks, for South Asian folks, from the original, overwhelmingly white population. Because the model, they fit this Cox regression model, which you can think of kind of like a linear, like a logistic regression. They fit this model to, their data. They did a good job of, getting a wide sample of people, training, validation, looking at it. But if you try to apply that model to a population outside of Framingham, tended to not work so well, right? So distribution shift is this idea of the distribution that you're looking at or using your model in the real world is different from the distribution that you train, validate, and test on. I want to briefly describe a case study for you to think a little bit about what's going on, and we'll discuss this a little further during discussion. So in this case, we're going to talk about the InterSalt study, which is a study that was trying to understand the relationship between salt and blood pressure. So they got 52 centers all over the world to each recruit 200 different subjects. And each center measured, everybody's salt intake, their blood pressure, their age. And they wanted to understand, whether or not, having more salt leads to higher blood pressure, whether you should be eating less salt. So here's what they did. They did a regression for blood pressure on age. And then from that, they got a coefficient, right? Which is like the rate of increase of blood pressure with age. Then they compared this slope to the average salt intake, right? So every center you look at the slope and you look at the average salt intake, right? With the idea that people in the same center, maybe they're in the same culture, they eat the same kind of food, more salty, less salty. And they compared the slope from this regression to the average salt intake, and they found a positive correlation. And their conclusion was, okay, so if there's a positive correlation, because the more salt, the faster your increase in blood pressure with age. So you should be consuming less salt to avoid high blood pressure. So I want you to take a couple minutes and think about what could have gone wrong with this study, and we'll go over it a little more during discussion. This video, I want to talk about another case study, which is a sleeping pill study from 2017. Or actually, there's many studies before that have generally shown that people who take sleeping pills tend to have higher rates of mortality, just overall, and even if you just look at mortality from specific causes. And even if you control for some confounders, that effect tends to persist. And then there's this 2017 study that says, okay, let's control for 300 different confounders all at once. And then in that study, they found, okay, if you control for all 300 confounders, then the effect goes away. There's no effect of sleeping pills on mortality. How should you interpret this? Does this, can you conclude a causal link here? Is this, what can you conclude from this study? So again, on your worksheet, write up your thoughts on, what could be happening here, what conclusions you can make, and we'll talk more about it during discussion.